Welcome to Financial Statistics. Today, we are diving into the fascinating world of discrete dividends. If you have ever wondered how cash payouts affect stock prices and complex financial contracts, you are in the right place. Let us build this understanding from the ground up. To start, imagine you are buying a fruit tree. If you buy it before the harvest, you pay for both the tree and the fruit. But if you buy it the day after the farmer picks the apples, the tree is worth less. In finance, a company's stock is exactly like that fruit tree, and a discrete dividend is the harvested fruit. A discrete dividend is a specific, known amount of cash paid to shareholders on a specific future date. The most critical moment in this process is the ex-dividend date. This is the exact day when new buyers of the stock are no longer entitled to receive that upcoming cash payment. Now that we understand what the ex-dividend date is, let us look at how it visually affects the stock price. On your screen, you see a graph with time on the horizontal axis and stock price on the vertical axis. Notice the jagged blue line representing the fluctuating stock price. Right at the dashed vertical line, which marks the ex-dividend date, there is a sudden steep vertical drop in the price. This drop is exactly equal to the dividend amount, labeled as D. This visual demonstrates why standard pricing models, which assume smooth and continuous price movements, break down when a dividend is paid. We have to account for this sudden drop mathematically. This sudden drop we just saw leads us to an important rule in financial mathematics. On the morning of the ex-dividend date, the current market price of the stock, known as the spot price, automatically drops by the exact amount of the dividend. This mandatory price drop is called the ex-dividend adjustment. Why must this happen? Imagine if the price did not drop. A clever trader could buy the stock the day before, collect the cash dividend, and sell the stock the next day for the same price, locking in a guaranteed risk-free profit. In finance, we call this arbitrage. All of our mathematical models assume that arbitrage is impossible, which is why this price adjustment is absolutely necessary. Before we can adjust our models, we need to know exactly how much that future dividend is worth today. This brings us to our first formula. We calculate the present value of the dividend using continuous compounding. In this equation, V represents the present value of the dividend in today's dollars. D is the actual cash amount of the discrete dividend. The symbol R is the continuous risk-free interest rate, and T is the time remaining until the dividend is paid, measured in years. Conceptually, because money paid further in the future is worth less today due to the interest you could have earned in a bank, as the time T increases, the present value V decreases. Now that we have the present value of the dividend, we can find the core value of the company. We do this by subtracting the present value of the dividend from the current stock price. This gives us the adjusted spot price, denoted by S star. S0 is the actual current market price of the stock today, and V is the present value we just calculated. This adjusted price represents the value of the stock's core business, completely stripping away the cash that is earmarked to be paid out. If a company pays multiple dividends, V would simply be the sum of all their present values. As the dividend amount increases, this adjusted stock price decreases. With our adjusted spot price in hand, we can now accurately price financial contracts, like a forward contract. A forward contract is a binding agreement to buy the stock at a set price on a future date. To find this fair forward price, F, we take our adjusted spot price, S star, and grow it by the risk-free interest rate, R, over the total life of the contract, capital T. We specifically use the adjusted price, not the original stock price, because the buyer of a forward contract does not receive any dividends paid before the contract matures. If the risk-free rate increases, the forward price will also increase to compensate the seller for tying up their capital. Let us see this with a concrete example. Suppose a stock is currently trading at $100. The company will pay a $2 dividend in exactly 3 months. The continuous risk-free interest rate is 5% per year. We want to find the fair forward price for a 6-month contract. First, we identify our given values and calculate the present value of the dividend. The dividend is $2, the rate is 0.05, and 3 months is 0.25 years. We plug these into our present value formula. The exponent becomes negative 0.0125. Calculating the exponential gives us a present value of $1.975. Continuing with our example, we now move to the second step, adjusting the spot price. We take the current market price of $100 and subtract the present value of $1.975. This gives us an adjusted spot price of $98.025. Finally, we calculate the forward price by growing this adjusted spot price over the full 6-month or 0.5-year duration of the contract. We substitute our values into the forward price formula and the exponent becomes 0.025. Calculating this yields our final answer. The fair forward price is $100.50. This means if you agreed today to buy the stock in 6 months, you should pay exactly this amount to prevent any arbitrage. So, we have successfully priced a forward contract. This brings us to options. Dividends heavily impact option pricing. A call option gives you the right to buy a stock, so you want the price to go up. A put option gives you the right to sell, so you want the price to go down. Because a discrete dividend forces the stock price to drop, dividends are bad for call options and good for put options. The famous Black-Scholes formula, used globally to price options, assumes that stock prices move smoothly, without sudden jumps. However, as we saw earlier, a discrete dividend causes a sudden, predictable jump downward. This completely breaks the standard Black-Scholes formula if we use the raw stock price. To fix this broken formula, we use the exact same trick we used for forward contracts. We subtract the present value of all dividends from the current spot price before doing any option math. Here we see the first step of the Black-Scholes formula, which calculates a variable called D1, measuring the probability of the option being profitable. Notice that instead of the normal stock price, we use S star, our adjusted spot price. K is the strike price, which is your locked-in buying or selling price. The symbol sigma represents volatility, measuring how wildly the stock price swings. By feeding S star into the formula, we mathematically pretend the stock does not pay a dividend, allowing the continuous math to function perfectly. This adjustment is not just for Black-Scholes. It is also critical for discrete dividend trees, often called binomial models. These are step-by-step models used to price options over time. If we try to build a mathematical tree using the raw stock price, subtracting a fixed cash dividend causes the branches of the tree to miss each other. We call this a non-recombining tree, and it is a computational nightmare because the number of branches explodes to infinity. To solve this elegantly, we build the entire tree using only the adjusted spot price, S star. Then, at every single node in the tree, we simply add the present value of the remaining dividends back in to find the true stock price at that specific moment. Before we conclude, let us look at a slightly harder example involving multiple dividends. A stock is currently trading at $50. The company will pay a $1 dividend in 0.2 years and another $1 dividend in 0.45 years. The risk-free rate is 5%. We want to price a 6-month call option. Before using Black-Scholes, we must find the adjusted spot price. Our strategy is to calculate the present value of each dividend separately. We start with the first dividend. The cash amount is $1, the rate is 0.05, and the time is 0.2 years. Substituting these into our formula, the exponent becomes negative 0.01. This gives a present value of $0.990. Now that we have the present value of the first dividend, we move on to calculate the present value of the second dividend. We use the exact same formula. The dividend is again $1 and the rate is 0.05, but the time is now 0.45 years. Substituting these values, the exponent becomes negative 0.0225. Calculating the exponential gives us $0.978. Notice this is slightly less than the first dividend because it is paid further in the future. Next, we find the total present value by adding the present values of all dividends that occur before the option expires. Adding 0.990 and 0.978 gives us a total present value of $1.968. We are now ready for the final step of this example. We calculate the adjusted spot price by taking the current market price of the stock and subtracting the total present value of the dividends we just found. We substitute $50 for the current spot price and $1.968 for the total present value. Performing this simple subtraction gives us our final answer. The adjusted spot price is $48.032. When you sit down to use the Black-Scholes formula to price this call option, you will completely ignore the real $50 stock price. Instead, you will plug 48.032 into the formula as your starting stock price, perfectly accounting for the two upcoming price drops. Now that we have used this adjustment in multiple scenarios, let us understand its real-world importance. Understanding discrete dividends is absolutely critical for anyone working in financial markets. If a bank ignores upcoming dividends when pricing options or forward contracts, they will systematically overprice call options and underprice put options. Smart traders would immediately notice this mistake and execute arbitrage strategies, draining millions of dollars from the bank completely risk-free. By properly adjusting the spot price, financial institutions ensure their models reflect reality, keeping markets fair and preventing guaranteed exploits. In fact, every major trading software in the world automatically performs this exact present value subtraction before running any complex pricing algorithms. We have covered a lot of ground today, so let us review the key takeaways. First, remember that a discrete dividend causes a sudden, predictable drop in a stock's price on the ex-dividend date. Because standard financial models cannot handle these sudden jumps, we must manually remove the present value of these future dividends from the current stock price. This creates an adjusted spot price that represents only the risky, fluctuating value of the company's core business. Whether you are pricing a forward contract, using the Black-Scholes formula, or building a binomial tree, this simple subtraction is the universal key to making the math work correctly. You now have the tools to handle discrete dividends in any financial model.